Okay, folks, I'm gonna talk you through this introduction to chemical kinetics, which kind of naturally follows on from our previous topic of energetics. They're kind of linked really well. And if you're asked what chemical kinetics is all about, you'd be quite right to say it's the speed of reactions. It's the study of the speed of reactions and what affects that speed. That's really what it's all about. Okay, and there are several factors that affect reaction rate, and I bet you know a lot of them already. In fact, this topic is something you have actually studied in quite some detail already at GCSE, and there's a few things to add on. So the first thing is chemical kinetics is the study of reaction rates. And one of the questions in the exam is often, define reaction rate. Now, if you ask that to a year 9, they'll say, oh, that's the speed of reaction. They're asking you for the definition of reaction rate. In other words, what is it a measure of? And have a little think about that now. You can pause the video for 10 seconds and think about what is reaction rate a measure of, okay? Yeah, well, reaction rate really is a measure of how much product is formed in unit time, or how much reactant is consumed, is used up in unit time. It's like in physics, when you're asked what speed is, it's the distance covered in unit time, isn't it, right? So in the case of chemical kinetics, it's the a measure of how much stuff, how much product is formed in a given time, or you can measure it as the rate of decrease of the amount of reactants, okay? So you can write it like this, okay? Delta meaning the change in, the amount of product. We're not going to specify the units yet, but the amount of product formed in a given time span, okay? Now, you could also measure it like this, the amount of reactant, the change in the amount of reactant in a given amount of time. I note the negative sign there, okay? Because that's going to decrease, isn't it, right? Okay, now possibly units of reaction rate. I'm sure you can guess what some of these units are. There's some possibilities here. It could be grams in unit time. It could be moles in unit time. cm cubed is good for a gas, amount of gas formed in a given time, the volume of gas formed. But usually in the exams, we talk about changing concentration with time. So the unit is mole per dm cubed per time, per second, per minute, whatever, okay? But there are lots of possibilities. Probably the two that you'll see most often in your exams are these two, the bottom two here, okay? Now, just to illustrate the point here, you can see that this is blue plus red giving green. And you can see, if you just follow this at time 0, then like 16 seconds or something, okay? And then you can see 33 seconds, the reaction is still going on. Some blue and red has not reacted yet. And even at 46 seconds, it still hasn't finished reacting, okay? Whereas in this case, you can see the reaction was over in about 33 seconds, okay? Started here with no green, then the green built up, and eventually you got maximum green, so the reaction was very, very quick to finish, okay? Now, this is a picture of me with a student who didn't do their homework. No, I'm only joking. This is an explosive reaction, and this one here is said to be instantaneous. It's immediate. You can't even measure the rate. It's too fast. No need to wait. Everything happens in like microseconds, and the reaction is said to be instantaneous. And here's another example of an instantaneous reaction: is precipitation. The very, very fast. It's a reaction between ions, plus and minus, and so the reaction is really fast. You can't really measure the rate, okay? Now, these are a few more reactions. This is a penny that's been put in nitric acid. This is the thermit reaction, and this is potassium in water. And they're vigorous, and they last like, minutes, or they are measurable, but they are quite fast. And then you've got kind of slower reactions. This might take a minute. This is the famous thiosulfate reaction. You might remember the cross on the paper in year 9. This takes about 40 minutes. This is a displacement reaction of silver being displaced by copper. silver being displaced from silver nitrate, and rusting, of course, takes months and months. So you know that some reactors are really, really slow. Now, there's lots of factors that can affect the reaction, and one of the the main themes of this topic is we want to know what these factors are and why they affect the rate. That's really important, okay? The other thing that will be new to you, this is quite new, is the idea of a reaction mechanism. And it can, reactions occur often in steps, in individual steps. And there's different numbers of particles that have to collide in each step, okay? If two particles collide, it's bimolecular. The molecularity is 2. If one particle is involved, it's unimolecular. The molecularity is 1. So they're kind of new words for you there, okay? So unimolecular, bimolecular, and termolecular. Termolecular is quite rare, actually. That's probably not going to happen very much, okay? So taking a quick look at that slide there, you can kind of read those things. And then, like here, for example, you have A plus 2B giving AB2. That's the overall stoichiometric equation. But you can see that this reaction is taking place in 2 steps. First of all, one particle of A collides with one particle of B to give this AB. That's step 1, and it's bimolecular. You can see 2 particles involved. Molecularity is 2. And in the second step, the second B particle then collides with the AB to give the final product. Now you can see that this and this can be crossed out. And so overall, the overall equation is then shown there, okay? But there are 2 steps and they're both bimolecular. So that's what I mean by mechanism, okay? Now, we all know that temperature affects reaction rate. If you turn the cooker up to a higher temperature, then the food cooks much more quickly. If you put milk in the fridge, then the biochemical reactions that make milk go bad, they slow down. So everybody knows about temperature. That's a factor that most students will know from an early age, okay? Who cares about reaction rates? Well, chemical engineers do. They have to know how to make reactions fast and efficient and economically viable. So the topic of kinetics is very, very close to the hearts of chemical engineers. Now, this is quite important. You see this before, reaction profile. And when you were studying energetics, the blue is the domain of energetics, the domain of thermochemistry, because all you care about is the initial and final state. This reaction is clearly exothermic, isn't it, right? There's a decrease in the enthalpy. But you don't care about the speed. It could take months, it could take seconds. You just care about the energy difference, the enthalpy change. But in kinetics, we care about the route. We care if this is time on the bottom here, then we care about what happens from the reactant to the product, what's in between, what's the mechanism in between. So that's kind of an interesting little take on reaction profiles. Now, you've probably heard this before, collision theory. Collision theory concerns the things that must happen for a reaction to occur. And the first most obvious thing is that particles must collide. They have to bump into each other. And when they bump into each other, you want bonds to break, and then you want new bonds to form. So when they collide, they must collide with enough energy. It's actually called activation energy, and that's needed to break the bonds. And the third one, which we don't mention much in the lower school, the younger years when you're taught this, is they must collide at the right orientation, the right angle. It's not always successful. Okay? So here we have examples of there is the correct orientation, the carbon atom must face the oxygen, you get the products, and all of these are all wrong for different reasons, so there's no reaction. Okay? Something often forms in the middle between reactant and product, and that's called the activated complex. Okay? Activation energy we've mentioned already. That must be enough energy in order to have a successful, fruitful collision. And this is the definition here, and you need to know that for the exams, okay? So it's the minimum energy required on collision for a reaction to occur. So here we are, successful collision. A is going to hit B, and there's enough energy, so there's a reaction. In this case, There's the correct orientation, A is facing B, but there's not enough energy for collision, so no reaction. And there we are, here's the reaction profile again, and we have the intermediate in the middle. There's partial bonding between A and B, and then the partial bonding between B and C as it breaks away, and then you get the final product. And this is called the activation energy. There's delta H, written as delta E here, that's delta, it's exothermic and delta H, okay? And there's the final products. So again, successful collision, but here, the collision's unsuccessful. The A is going to hit the atom C, and there's no reaction, okay? So that wouldn't work. So now that's the end of the kind of introduction to the idea of kinetics and reaction rate. And we'll go on to look at rate curves on the next mini video, okay? But you need to digest all that now and visit the relevant Firefly page, the introduction page, so that you can get some idea of the vocabulary used, the definitions and the terms in this topic, okay? There you go.